Aloha, everyone. Welcome to this joyous morning. It's a good day. So we are here for Odachi's thesis defense. And before she gets started, uh, just a little bit. Um, so I first met Naya as an undergraduate, in a couple different classes, but didn't know her that well. And then she graduated with highest honors as a double major in art and geography, which to my knowledge is the only one that's done that. Maybe there's some others, uh, but I was always impressed with her. And then she graduated. Oh, great. And then a little bird said, "Oh, I've got this daughter, and she might need a job." And so I
You're
said,
not supposed to say that. I don't think she knows that. No, I did not.
and so was able to find a part-time position for Naya in the SDev lab, and quickly it became very obvious that she's a very valuable person and very helpful in our efforts to monitor and look at rapid Ōhi death. And so was able to have her in the lab for a number of years, also through the Kupu program, Kupu Ainakor. And then she decided to get a master's degree. And so that was wonderful for us. But even before the master's degree, which she's about to share some of the work that she's done in that, she's been making real contributions to our efforts against rapid Ōhi death. Like as an undergraduate, recent, major, and then as a technician in the lab. And so I would think, and to be honest, more than, although all my students are wonderful, and they're all doing great things, but in terms of impact on conservation in Hawaii, Naya has had some of the greatest impact that I've seen. So it's really been an honor to have you as a student. And so I'll let her get started, but I have a lay I'll give you, and then we can. Hopefully it will fit on your all the other ones you have, but congratulations. Okay, so without further ado, I'll turn it over.
Please close all these notifications first.
Is JP Friday is one of the people.
He is.
Okay.
Okay. Thank you, Ryan, for your very nice words. And I would not have done this master's program at all without you. You reminding me every year that the application is open. So yeah, thank you so much for giving me this opportunity and supporting me so much through all of this, and all of you. Thank you. So yes, I'm Naya Odachi. I'm part of the Tropical Conservation Biology and Environmental Science graduate program at University of Hawaii at Hilo. I'm part of the thesis track and will be presenting my research on high-resolution satellite imagery, an alternative method for the detection and monitoring of rapid Ōhi death in Hawaii. I'd like to first acknowledge my committee members, Ryan Perroy, Jonathan Price, and JB Friday. I'd also like to thank Brian Tucker, who is a part of the Pacific Cooperative Studies Unit, Rapid Ōhi death, and Dustin Swan, who's part of the Big Island Invasive Species Committee, for providing the digital mobile sketch mapping data and supporting my research with field surveying. A huge mahalo to Pat Perez, who's on Zoom. She's an integral part of the spatial data analysis and visualization lab, and without whom I could not complete the deep learning portion of my research. I'd like to also give a shout out to the SDev lab, my fellow TCBES graduate students, and a big thank you to all my family and friends who have supported me along my graduate journey. So most people already know what ōhia is, but we'll do a quick introduction again. ōhia, or Metrosideros polymorpha, is considered the most dominant native tree species in Hawaii. It can be found from sea level to 2,500 meters in elevation, with the name polymorpha describing the range of morphologies that ōhia can exhibit. ōhia is a keystone species that provides habitat to endangered forest birds, endemic flora and fauna, and is essential for Hawaii watersheds, as well as being deeply rooted in Hawaiian culture. In 2010, the fungal disease rapid Ōhi death, or ROD, began to cause widespread mortality of ohia across Hawaiian Island. ROD consists of two identified pathogens, Ceratocystis lukuohia and Ceratocystis huliohia, and has killed countless ohia trees and continues to devastate our native ohia forests. Ceratocystis lukuohia is considered the more aggressive and the primary cause of widespread ohia mortality. ROD affects the tree's vascular system, and it stops the water from moving to the tree's crown. This results in canopy color change, which can be used as an indicator for ROD infection. These images show canopy color progression as trees begin to die using different remote sensing platforms. The top set is imagery collected via small unmanned aerial systems or drones at a less than 1 centimeter resolution. The middle set is helicopter imagery at a less than 5 centimeter resolution, and the bottom is high resolution world view satellite imagery at a 50 centimeter resolution. The red-brown phase is optimal for tree identification using remote sensing methods, since there is limited explanation for bright red or brown full canopy in Hawaii. However, this phase only lasts up to 3 to 4 months. Additionally, there are other reasons ohia may die, so field sampling is required to confirm positive infection. Currently, there exist multiple remote sensing efforts for monitoring ROD in Hawaii. One of the finest resolution methods is high-resolution aerial photos collected using drones or helicopters. This method is used for high priority areas due to the spatial limitation. There's also semi-annual helicopter-based digital mobile sketch mapping, or DMSM surveys. These occur multiple times a year and include an island-wide flight and a few priority flights focusing on areas of concern. However, these flights can be hazardous and variation occurs in data collection due to the interpretive quality. There also exists efforts using laser-guided imaging spectroscopy. The flights have occurred from 2016 to 2019, but they're very expensive and have multiple difficulties for analysis and post-processing methods. Lastly, initial efforts looking at Sentinel-2 moderate resolution satellite imagery found red and dead mortality could be identified, but required significant time for evaluation. The resolution is also pretty coarse, as you can see. Those blobs are supposed to be trees. Although these methods are useful for ROD monitoring, all have some type of temporal, spectral, or fiscal limitation. My research focuses on the applications of high-resolution satellite imagery, specifically Maxar, WorldView 2, WorldView 3, and GeoEye-1, as an option for ongoing ROD monitoring. This multispectral imagery covers hundreds of thousands of hectares and has a resolution of up to 50 centimeters. The bottom two images show the spectral profiles of a red symptomatic tree and a green tree. A total of 8 spectral bands are available for this type of imagery. To address this, I have 3 research questions, which is quite a lot. First, what is the positive detection rate based on confirmatory laboratory testing of samples collected from ROD suspects identified from high-resolution satellite imagery? Second, how well do digital mobile sketch mapping, or DMSM surveys, and satellite imagery datasets compare in terms of identifying mortality likely associated with ROD? Lastly, how accurately and precisely can deep learning programs, specifically DeepForest and ENVI deep learning, identify individual suspect ROD trees in satellite imagery? Let's address the first research question. What is the positive detection rate based on confirmatory laboratory testing of samples collected from ROD suspects identified from high-resolution satellite imagery? To start, all satellite images are pre-processed in NV5 Geospatial's ENVI program. They were all pan-sharpened and atmospherically corrected. This applies to all imagery moving forward and used in this research. To identify individual symptomatic trees, I systematically went through these images and manually marked the center point of each canopy to record their geographic locations. This image on the left is from August 2021 and is one of the initial efforts to identify individual suspect trees in satellite imagery. I only looked for the brightest red or brown phase trees and identified a total of 446 suspects. Moving forward, we focused on areas of interest on Hawaiian Island, mainly Hakalau Forest National Wildlife Refuge, the Hilo Forest Reserve, Kiha section, and Pu'umaka'ala Natural Area Reserve. These are high priority forest areas where rod infection is of high concern. And so the Pacific Cooperative Studies Unit Rapid Ōhi Death Manager and Big Island Invasive Species Committee requested identified suspects to direct their field sampling efforts. 5 images between 2021 and 2023 were used to identify a total of 1,211 suspect trees. The geolocations of each tree were sent to BISC for subsequent sampling and then sent to the U.S. Pacific Basin Agricultural Research Center for Ceratocystis confirmation. The left image shows examples of suspect trees identified in worldview imagery. Here are the results of Hakalau and Kiha shown above. The black dashed lines are the existing fence lines, and the gray solid lines are the reserve extents. Sampling results are categorized based on the tree being within fenced or unfenced areas, with the circles signifying trees in unfenced areas, and squares are trees in fenced areas. The red symbols are trees that were sampled and resulted in Ceratocystis lukuohia positive detection. The gray were sampled and Ceratocystis was non-detected, and the white were visited but not sampled. A couple trees were not located, and those trees are marked with the crosshairs. This shows the trees visited in Pu'umaka'ala with the same symbology. As you can see, all of the sampled trees came back non-detected for rod, and a few of the trees were visited but not sampled. Let's break it down by numbers. Of the 55 suspect trees that were visited in the field, 94.5% were successfully located. Of the successfully located 52 trees, 98.1% were identified as ohia. Laboratory results show that of the 35 sampled trees, 40% came back positive for Ceratocystis lukuohia. On the bottom right is an example of the satellite images used for sampling and the results that came back not positive for rod, as well as the samples that did come back positive for rod. As you can see, they are all symptomatically red, but for some reason, some were non-detects. Although overall positive detection was not high, breaking it down by unfenced and fenced areas provided interesting results. Of the sampled suspects located in fenced areas, 11.8% were positive for lukuohia. Of the 2 trees that came back positive, the first tree is the only positive detection within the managed portion of Hakalau Forest National Wildlife Refuge. The second tree is also located in a fenced section, but this area is not currently managed and has known ungulate activity. Of the sampled suspects in unfenced areas, 66.7% were positive for lukuohia. Although this is not an exhaustive dataset, it does align with existing findings that fenced and ungulate-free areas exhibit lower ohia mortality. In an attempt to increase my dataset, I requested GPS points of sample results from previous years and did my best to collect satellite imagery from 3 to 4 months prior to the sampling date. This was difficult since imagery was cloudy or scarce. From the images I was able to find, I identified potential suspects without looking at the sampled tree locations to minimize my bias. When comparing the two, there was a shift between the datasets. But since not all symptomatic trees were sampled, I could not confidently realign them for comparison. In conclusion, ohia trees suspected of pathogen infection can be identified in high-resolution satellite imagery. These points are useful to direct field surveying and sampling in remote areas. In addition, these satellite-derived sampling results support theories that fencing is a method to reduce ungulate-caused rod dispersal. Moving on to larger scale mortality patterns, we get to my second research question. How well do digital mobile sketch mapping surveys, or DMSM, and satellite imagery datasets compare in terms of identifying mortality likely associated with rod? Pushing past single tree identification, I wanted to explore the usefulness of high-resolution satellite imagery for identifying annual mortality patterns to map the spread of rod. Since rod originated in Puna, I focused on East Hawaiʻi to analyze the spread of mortality from the origin. For each year of the time series, satellite imagery was chosen within a 3.5-month time frame because I was looking for that vivid red or brown crown that lasts only up to a few months. I wanted to limit the temporal aspect of the imagery. However, the month period varied between each year depending on image availability and fullest area coverage, as can be seen in the bottom visual. To identify areas of mortality, images were first displayed in true color. I would systematically go through the satellite image using these grids and mark organic polygons to cover areas of mortality. To be included in this data set, these mortality clusters must contain a minimum of 40 trees per 100 hectares. Here is an example of the satellite images that were used from 2016 and the identified mortality of the same year. Clouds were a consistent issue, as can be seen on the left image. In this instance, there was another image covering that section, and I could use it to substitute and identify the mortality from it instead. However, this was not always the case, and some years there was quite a bit of cloud coverage. I then compared the satellite data to digital mobile sketch mapping, DMSM, identified mortality. This biannual forest mortality mapping began in 2016. Survey crews would fly in a helicopter and use tablets to mark individual dead trees with the red or brown symptomatic crown. Sometimes polygons would be used instead for larger areas of mortality where numerous trees were dying and could not be marked individually. For each polygon, damage severity is reported as a mortality class with a percentage range. Very light, 1 to 3%, light, 4 to 10%, moderate, 11 to 29%, severe, 30 to 50%, and very severe, greater than 50%. The map on the left showed the 2016 DMSM flight coverage in dark green and the light pink indicating DMSM identified mortality. I began identifying mortality from satellite imagery beginning in 2013. However, DMSM surveys began in 2016, so I could not compare the datasets from 2013 to 2015. These images show the mortality identified in satellite imagery in the East Hawaiʻi area. The red polygons show recent mortality. The yellow-green line indicates satellite imagery coverage for that year. The white is cloud cover that obscured visibility. As you can see, mortality areas slowly started to increase over the years. From 2016 to 2021, I've added the DMSM dataset with the satellite dataset to show the overlap in coverage area and mortality area. We have the same symbology of the darker red for the satellite identified mortality as before, and the added light pink DMSM identified mortality. In 2018, you can see there was very limited satellite imagery coverage. This was due to high cloud coverage and very limited imagery acquisition throughout the year. The time when surveys were conducted also did not align between the two datasets, and this is likely the reason for variability between the two. Here's the continuation from 2019 to 2021. As you can see, satellite imagery has greater coverage in most years. However, there are gaps in certain areas where images were not clear or available. And in the later years, the DMSM surveys did not cover portions of Puna. Since ROD was known to occur there, these areas were not prioritized. This shows the same data as in the previous slides, but not as pretty and more quantitative. Here is annual coverage area and identified mortality from DMSM surveys and satellite images. The solid lines are the area of identified mortality for each dataset and are associated with the y-axis on the left. The dotted lines are annual area coverage for each method and are associated with the y-axis on the right. Satellite coverage area was greater in all years except 2018. This year had limited clear imagery availability and within that 3.5-month time frame I was looking at. Annual identified forest mortality is also greater in satellite surveys, but this is likely due to the fact that there was more overall area coverage. This research shows that high-resolution satellite data can be used to identify landscape mortality patterns, with satellite datasets showing similar annual mortality trends as those identified in DMSM surveys. The datasets are not a one-to-one comparison due to the spatial coverage variations. Additionally, temporal variations can greatly affect the datasets due to the red-brown mortality phase occurring for only a few months. The DMSM flights occurred throughout the year due to weather conditions and crew and pilot availability. In comparison, the satellite-derived mortality patterns were from a 3.5-month time period based on clear and available images. Both datasets are very useful for showing annual forest health patterns. However, they do have their own limitations. DMSM flights are very useful since they can identify new outbreaks and can be scheduled around weather events. However, they are subjective in nature, and spatial coverage is limited and does not cover the entire island. Additionally, helicopter flights are costly, can be hazardous for survey crews, and produce significant emissions. With satellite imagery, you can go back and double check mortality, but cloud-free imagery is difficult to obtain for certain parts of Hawaii since we do get quite a bit of haze and clouds during significant portions of the year. Imagery collection is also not within our control, and thus clear imagery for areas of interest may be limited. That's part of the reason the analysis did not extend beyond 2021. Using both datasets together will provide the most accurate story of annual forest mortality trends. Due to limited satellite imagery collection, I suggest using DMSM flights as the primary source to report annual mortality, and using satellite imagery to supplement as needed. After all of this, I got very tired of looking at dead trees and manually identifying things because it takes a lot of time. So that brings us to my third research question. How accurately and precisely can deep learning programs, specifically DeepForest and ENVI deep learning, identify individual suspect rod trees in satellite imagery? For the automated detection of Rapid Ōhi death, I use deep learning object detection. Deep learning is a type of representation learning where raw data is given to the machine and subsequently features of interest are identified. Specifically, object detection identifies the precise location of objects using shape, area, or color characteristics. This is extremely useful when processing large quantities of remotely sensed data. To create object detection models, I use two deep learning programs. The first, ENVI5 Geospatial's ENVI, and deep learning extension, is TensorFlow-based and uses a RetinaNet convolutional neural network. This can be trained on RGB, multispectral, or hyperspectral data. The second, DeepForest, is a PyTorch-based and also uses a RetinaNet convolutional neural network. However, it is a Python package that has been pre-trained on RGB aerial imagery. Therefore, it is only able to use RGB images. ENVI was chosen because it was marketed as user-friendly with no programming required, as I do not know a programming language. The SF lab had already been using DeepForest for rod detection, but it was being used for helicopter and drone imagery, so we wanted to expand and test its ability on satellite images. Both deep learning programs were provided the same images and annotations for training and validation. 5 images total, covering varying portions of East Hawaiʻi, contained a total of 1,434 annotations and were used for model creation. Images ranged from 2020 to 2023 with resolutions between 31 and 50 centimeters and were either from WorldView 2 or WorldView 3 satellites. The bottom image shows an example of red suspect trees included in annotations. I know this is a lot. You don't need to read it all, I promise. The basic workflow follows the same path using different program methods. The ENVI process is on the left and the DeepForest is on the right. The overall workflow includes manually identifying suspects using points. Those points are then converted to bounding boxes that encompass the tree crowns and subsequently fed into the object detection model with the corresponding images. The images for training and evaluation were all pan-sharpened and atmospherically corrected. For the images, there are a couple specific differences. For the DeepForest workflow, images were exported as the RGB version since that is the only image type that is compatible with those 3 bands. Images are then segmented into 1,000 by 1,000 pixel portions before being used to train the object detection model. For ENVI, images had a linear 2% stretch applied to the visualization. What does that mean? Well, there's this option in ENVI that allows you to have a stretch type applied so an image can be enhanced. On the top left is the default optimized linear that the satellite images open in ENVI with. On the bottom left is the linear 2% stretch applied to the same image. Without the linear 2% stretch applied, the model produced results as seen on the right. Each red box is what the model thinks is a symptomatic tree, which is obviously probably not correct. After consulting with the NV5's deep learning specialist, he suggested applying the linear 2% stretch to images prior to training to improve model creation. And this did end up fixing this issue. After models were created for each method, a separate test image was then used to run inference and afterwards visually evaluated. It's important to note that this image was not included in the model training. Evaluation metrics were calculated using ArcGIS Pro 3.2's compute accuracy for object detection tool. ENVI and DeepForest programs can easily calculate precision and recall, but ENVI does not provide a way to calculate additional metrics for model performance. DeepForest can provide the information, but with additional code. However, we wanted to use ArcGIS Pro so we could ensure the metrics were calculated in the same way and were comparable. Included in the evaluation metrics is precision, recall, mean average precision, or MAP, and an F1 score, which were calculated for each model. So let's break each of these down. To calculate precision and recall, an intersect over union, or IOU threshold, was set at 40%. IOU is the ratio of overlap in the area of union for each ground truth and prediction bounding box. Predictions are considered a true positive if the IOU falls above the threshold, and a true negative if below the threshold. Using the true positives and false negatives from the IOU threshold, we can then calculate precision and recall. Precision is the true positives over true positives plus false negatives for all predictions. Recall is true positives over true positives plus false negatives for all actual ground truths. From the precision and recall, the mean average precision can then be calculated. The mean average precision is a singular metric to evaluate model performance and is the average calculation of the average precision, which is the area under the precision recall curve. Lastly, the F1 score is calculated. This is an additional analysis metric and is the harmonic mean of precision and recall. While MAP emphasizes location precision, the F1 score focuses on accurate counts of ground truths and predictions. Here are the results of 3 of the models for each object detection method. The top table shows the evaluation metrics for ENVI based on a 60, 65, and 70 epoch model. The bottom shows the evaluation metrics for DeepForest from the 23, 24, and 25 epoch models. The best precision, recall, F1 score, and MAP for each method are signified with a darker color. Although the variations within each object detection model is interesting, we're focusing on comparing the two. The ENVI object detection models are resulting in significantly lower F1 scores and MAP compared to DeepForest. The total prediction column is the quantity of all predictions made by the model. As you can see, ENVI makes way more predictions compared to DeepForest. Here are a couple examples of inference results greater than or equal to 50% confidence from ENVI and DeepForest models. The top 2 and bottom 2 images show the same extent. The red boxes are DeepForest inferences, and the blue bounding boxes are ENVI inferences, with the yellow boxes are what I identified and are considered the ground truths. The values next to the boxes are what the model's confidence scores were. In both image sets, ENVI obviously is identifying more trees compared to DeepForest. You may also notice that when both identify the same tree, ENVI has a tendency to have a higher associated confidence value. This can be seen in the top image where DeepForest identification has a 70% confidence value and ENVI shows an 85% confidence for the same tree. This happens again in the bottom with DeepForest at 55% confidence and ENVI at 74% of the same tree. When viewing the confidence value, a threshold of 0.5 or 50% was applied to visually compare the results. This is because ENVI predictions were in the thousands and included many false positives, such as these clouds, which are mistakenly being identified as suspect broad trees. In contrast, DeepForest results would actually benefit from decreasing the confidence threshold. The top left image shows DeepForest results filtering out anything below the 50% confidence, and the bottom left is the same extent and includes all predictions made by the model. This is identifying many of the ground truth yellow boxes compared to when the confidence threshold is increased. We also have instances where trees are being identified by the model, but they were not included in the evaluation dataset. The evaluation dataset only included the reddest of the red trees as identified by my eyes. However, the trees identified by the model do look symptomatic to me, even if they were not the reddest of the red. This brought up the question of how to quantitatively characterize a red tree. Due to color representation variation between monitors, as well as analyst interpretation, having a consistent threshold for what is considered a symptomatic tree would help to reduce variability. To look at the redness value, the excess red index was calculated for each training image and used to calculate excess red values across trees in the training model. Each box plot shows the excess red values of trees used in training for each of the training images. Results of the Kruskal-Wallis rank sum test showed a significant difference between excess red values of trees among datasets. The brackets with the asterisks indicate significant differences in medians between paired training image data using a Wilcoxon rank sum test. This shows that redness variation can occur between images, likely due to sun elevation, acquisition time of day, which makes establishing a set threshold for redness value very difficult. While images were atmospherically corrected using the QUAC method in ENVI, this may not have been enough to make them uniform. In addition to differences between the images, there is also variation of excess red that occur when a stretch type is applied. These images show the excess red plus RGB values of the same pixel when different stretch types are applied. While the linear 2% stretch improved ENVI model performance, it resulted in a decrease of precision and recall for DeepForest models. The optimized linear was used instead. Overall, both methods have their pros and cons. ENVI is able to use RGB, multispectral, and hyperspectral data. Learning modules are also available to guide users, and ENVI is able to pre-process the satellite imagery. However, the program is expensive and with added costs for additional extensions. And additionally, the visualization stretch type complicates model performance and pulls into question the program's ability to use the data pixel values rather than the stretch type values. I also have reached out to tech support to share my results, but they have not responded with any suggestions on how to improve this. So we'll see. DeepForest, in comparison, is open source and therefore it's free. It's also pre-trained on tree crowns, which is ideal for this research. But it's only able to use RGB spectral bands, and you must be proficient in Python. In conclusion, suspected rod trees can be identified by object detection models, with DeepForest significantly outperforming ENVI models, and were much more conservative in identification and confidence thresholds. Establishing the best confidence thresholds is important and may differ depending on which method is used. Since the ultimate goal is to use these predictions to direct field sampling, reducing false positives is necessary so time is not used looking for false suspects. These model-identified suspects should eventually be visited in the field and sampled to see how accurate the model confidence compares to sampling results. This will help to establish a threshold for priority individuals, which can then save field crews time. Future research can focus on normalizing satellite images for training and inference, and identifying a quantitative value for suspect trees to include in model training. In this research, I focus on the red-brown phase because that's what we're looking for field sampling. However, automated identification could also focus on other stages of ROD, such as the white phase. Since these satellite images cover varying vegetation compositions, additional training data may be needed to improve model performance. This will also be necessary for applying automated detection to the rest of the state of Hawaii. Each island's terrain and vegetation is unique, therefore more training data will be needed and likely a unique model created for each island. From all we've discussed, what we have seen is how useful satellite imagery is for ROD detection and monitoring. First, individual suspect trees can be identified from satellite imagery and direct field sampling, especially in remote areas. Secondly, satellite imagery complements existing annual DMSM datasets and additionally fills in spatial gaps to provide an extensive view of mortality patterns. Third, DeepForest should be used over ENVI for automated detection efforts, and further work is necessary to refine detection models for field sampling. Overall, satellite imagery is a safer alternative to helicopter-based monitoring and can cover larger areas, although cloud coverage and limited imagery availability continues to be a limitation. High-resolution satellite imagery can be used to support ongoing monitoring, and as it becomes more regularly available, it is a viable alternative to identify new outbreaks and map annual mortality trends. Each method is very different but useful in their own way, and ultimately, automated identification will make ROD suspects easier and faster to locate. Although ROD occurs across most of Hawaii Island, consistent monitoring can provide insight into trends of broad spread associated with fencing, storm events, or other occurrences. It also allows for rapid response in areas of high concern where ROD is limited, such as Hakulau Forest Wildlife Refuge. Lastly, continuous monitoring on other islands is necessary to track forest health and identify new outbreaks so land managers can react quickly and limit spread as much as possible. Thank you very much for listening. I know that was a lot of information. It was a lot of work and time, so if you have any questions, please ask me.
You got a question? Maybe repeat what he says.
Yeah.
Yeah, so fantastic about that. Incredibly see this working. It sounded like all the training that was put into the two algorithms was your annotations.
Yeah, all of it was my annotations from satellite images.
Do you have a chance to train with different person's annotations and see how different results may be?
So the question is if we can have someone else identify trees and use those training data. Well, I guess it's up to Ryan if he wants to hire someone else to do broad annotations. No, we didn't get that opportunity because it was mainly me working on Rapid Ōhi death in the lab. But that might be interesting.
Do you have a sense of how you're, so this is our old game, right? This is tree reference.
Yeah.
So I'm so curious, like how a different person's perspective may result in a different model or the same model.
Yeah, and I know there's been efforts looking at other types of forest mortality to like validate using other people's opinions, but we haven't done that with ROD, mainly because there's limited workers, but we could look into that and maybe that would affect model creation. I'm not sure.
Hopefully not.
Hopefully not. Hopefully we're pretty good. We'll see. Yeah.
I'm just curious about the cost associated with like the satellite programs and the. Is it a lot or is it a little? I have no idea.
I'm not sure exactly. You might want to ask Ryan or Brian might know.
So it kind of depends on the getting the educational discount, which is not that cheap. So it's thousands and thousands of dollars. I'll put it like that.
Every year or.
If you want to keep up with the most recent release, then yes, but you can certainly reach out to them to get a quote or such. But I mean, based on some of the results Naya showed, the at least for the machine learning part of it or the object detection part of it. The performance of the one that we paid money for was much worse than the performance of our open source.
Right, thank you for this amazing wisdom. The others from the Netherlands did for 4 months. I was wondering the comparison you showed between the helicopter observations and the observations were they normalized by the area that they both cover because it showed like different cover rates. It sounded like they were not
Yeah. So for the digital mobile sketch mapping surveys,
just was
Yeah.
what you showed the areas, the area comparison, are they biased by the various coverage of data?
yeah, there might be bias, and it's also very difficult to nail down an exact area coverage because when you're in the helicopter, it's hard to see far out, and unless you know the terrain, which BISC does know the terrain, there is variation, like how far this forest area may end, or there may be a fence that they can identify and be like, okay, that's about 1-2 miles out. Sorry, there's a lot of slides. Let's go around. Here. There we go. This map.
No,
More back.
The next graph that shows the comparison. So I guess after this.
Oh. This one.
we showed different power rates,
Mhm.
or maybe the different power rate with different areas.
Yeah,
It may affect the comparison. I was wondering whether you normalize.
I did not normalize it for this. Ryan and I had talked about it, but because the coverage areas are so different, it would, I feel like, significantly decrease both coverage area and mortality because there's so little overlap in certain sections.
It may depend what you want to show. Whether you
Yeah,
want
it depends what you want to look at.
Lines and normalizing makes sense.
Hmm.
Look at the overall coverage
Yeah.
on mortality.
You go back one. So you could only look at the places where they do overlap and then look at within the right? So that would be enough.
Exactly. I'm saying you have a better understanding whether the two data sets align.
Yep.
I think at one point we did create those graphs. They're somewhere deep in our hard drive somewhere. Any other questions?
Not trying to go through the slides or anything, but with the automatic learning, is there a possibility when like in vases or flowering that are red flowers, it can detect that?
That's a good point. At least when I was visually seeing how it was doing, I hadn't come across that. But definitely identified quite a few patches of red dirt, some red roofs. And yeah, even in helicopter imagery, like recently there was a heli flight that covered portions of volcano and like all of the cherry blossoms were blooming. And I was like, whoa, you usually don't see that because we don't fly at that time of year. And I was like, that's kind of new. So it could definitely pick up different trees that are just blooming or flowering that may be incorrect.
So time of year will have a big factor in it.
Yeah.
Thanks.
Yeah, I mean, I talked to Ryan yesterday about the techniques that you use to identify the red flags. Only lasts for a couple of months and you understand them and you stay at an annual temporal resolution. And if you're lucky, and then you have some help. What is your understanding of how much you omit using that high resolution data and like the annual imagery? Say I thought you omit because you don't see that red flags if you only look.
Yeah, so because we're looking for only that red brown phase, like if we were looking at total dead trees overall of Ohia, probably the majority of East Hawai would be included. But yeah, we're focused on that red brown phase because we're trying to use it for sampling purposes. But there's a lot of dead Ohia trees. It's very, very sad.
We have,
Things you omit a lot because of the temporal resolution you're using.
Because of the
Because you only have images once a year. So it's red and brown phase, it's.
Yeah, we're definitely missing trees that may be red in a different time of the year that we might not see in the images we're currently looking at.
JB Friday shared something in the chat, and excuse my mispronunciation. Can you read it, maybe? Oh, okay, maybe
I don't know
not.
if I can do better than you.
Sometimes senescent red leaves of jalna trees, Terminalia myriacarpua, sorry, have been misidentified as Rod Ohia trees. The jalna was one of the favorite trees of the territorial foresters back in the day. So just sharing another possible misidentified tree.
Yeah.
But maybe to respond to your point, honestly. So, I mean, presumably we're getting, a third to a quarter of the red trees over any 1 year period. With what's been shown here.
I mean, I'm from a group where we use a lot of like dense sample data, but not that high resolution data. We work a lot at the sentinel level, and I would hypothesize that even though you have a quarter spatial resolution, by using like the sense, temporal sampling, you can really look into the temporal signature, those mortality events happening on the ground stage, back stage, and everything. And use that, and also use that to separate it from other more natural blooming, clustering events. Like
I think there was efforts by an organization to look at Sentinel-2 imagery, and they were using, I can't remember exactly what they were using, but they did find they can identify the red-brown phase, but I think there was a lot of time and effort that needed to go into the validation portion, and also their research was limited in time, so they didn't do additional work. And they did suggest that like a longer time series analysis rather than like one snapshot of forest health would be better, so you can see the changes in forest over time.
I guess two questions where they combined. What do you think explains the difference in ENVI versus DeepForest, or how big they are? What bands was ENVI looking at, or that DeepForest did not? Were those bands resolution different than the RGB bands?
No, all the resolution's the same. ENVI uses all 8 spectral bands available in worldview imagery. So it includes like infrared, NIR1, NIR2, the RGB plus like coastal blue, near red. So it's supposed to include much more, but there's that question about the linear 2% stretch that we keep coming to, because supposedly they're supposed to use the data pixel value, but because I was told to apply the stretch and then use that as the input data, we're like, why is it using this visualization way rather than the actual data pixel value? So we're told it can use multispectral imagery, but we're not, I don't know. You'd have to probably look at the coding language and read it and see what it means. Yeah.
Did you ever compare just RGB in ENVI to RGB plus the bands?
That's a good point. I never did. That might have changed the results, but ENVI loves its clouds and broad trees. Yeah. That's why I think I saw you here.
yeah, it was kind of a follow-up to the question already. So, in thinking about shooting this, I was just looking at one shot per year. You could have also identify pretty easily dead opiate trees, and so by going per year, you can quantify how much you miss. It's an effort being done to monitor that.
Not to my knowledge.
So for the drone and helicopter imagery, we have looked at taking at these different phases and then being able to detect those. For Nai's work, she was really focused on that red ground phase as a means of supporting field sampling techniques and such, and getting that information out to the field crews. But what do you think, Nai? Do you think there's good potential to use this to get at the white?
Yeah, you can definitely see the changes in the white, but with something else that we've had an issue with for helicopter drone imagery is like once the tree gets to that fine white stage, it's pretty vibrant, pretty white, but as time passes, you'll start to see the branches fall off. So it'll become this skeleton. So you might start picking up like the green underneath, so the understory. So that then is no longer counted as like dead forest. Yeah, and then also this was focusing on like the red brown phase, so it could be compared to the DMSM mortality. So, and their flights occur very throughout the year. It's not consistent between years, and it's not consistently within 1 month. So we're both capturing very different time frames of forest health in Hawaii.
I got one last question. Sorry.
Yeah.
Do you feel like the deep learning is a place where you were trusted to find the first symptomatic tree?
DeepForest, sure, but I would also say that I double check. I'd go in and like validate before I send it off to the samplers, because I don't want to send them to like a patch of red dirt, because that's what it thinks is rod.
That's a really big deal.
Yeah.
That's a
Yeah.
yeah.
Another question about, I'm curious if you have issues with the very sudden information angle, factor on it. So whether they were all acquired at the same time.
Yeah, no, they were not acquired at the same time of day. So definitely the areas where, like when the sun is lower, there's more shadow cast, and that can complicate what looks to be red. So like myself visually, sometimes it's difficult. Definitely for the deep learning portion, it was identifying shadows because it thought it was a red tree. So that is an issue.
I was thinking about it. With what little I know about AI and deep learning from past experience, would it be possible for you all to take, there's no cure for rods, so the trees you identified, if they are, they will die, probably next time 40 itself.
Mm-hmm.
These 2021 red trees compared to 2024. And
Yeah,
see
those trees are dead.
Since, yeah, the
Yeah.
compare the positive is now dead.
Mm-hmm.
With that,
So it was actually interesting because I think there was a few single trees I identified and in Hakulau, and I'm not sure why, but it was like in 2021, and they went back later, like a couple years later, to go visit those same trees, and then that's when it still came back positive for Rob. So, and it was, I guess, still within that time period of not being completely dried out. So it could result in a positive detection. So I'm not sure. You could definitely.
I was just thinking with like AI to teach it better, like to confirm.
Oh, like to compare two different
Yeah, like,
images.
yeah, like in 2019, said this, like the AI said
Yeah.
this was dead. And compared to 2024, it has brought, and 2024 is dead.
Yeah, I think
it's a positive.
we'd have to do a different model depending on what phase we're looking at.
Just how we used to teach things, but
They don't come back over the red. You never see a red tree turn green.
No, I don't think I've ever seen a red tree go back to green.
Any other questions? And then anybody online with any questions?
No, none.
Okay, so I think with that, we can just, thank Naya for a wonderful presentation and chat with her a little bit, and then the committee will talk with her afterwards. So, right on. Thank you so much, Naya.
Thank you.